welcome to the lab. Now let's talk about light. Now this is the Hubble telescope, launched in 1990, and we've been using it for about 30 years now. And we've been using it to see stuff in space, because that's the only thing you need a telescope for. Now, in 2021, we launched a brand new telescope called the James Webb Telescope. It looks like a beehive. What was the main difference for needing to replace the old telescope? What's the largest difference between the James Webb Telescope and the Hubble telescope? It's because of the light they can see.
What the heck is that supposed to mean?
Now, look at this graph. This graph currently shows the light spectrum. This is the range in which humans can see. This is the range in which humans cannot see. The range in which humans can see is visible light. Anything outside of this range is invisible light. The Hubble telescope could originally only see in visible light, meaning whatever it saw, we could also see too, presumably if we were close enough. However, the James Webb telescope can see things in infrared light, meaning it can see things in a different way, or it can see things that were completely invisible to us originally, including planets and galaxies.
So you're saying there's like invisible galaxies and stuff?
Yeah, I'll just get to it later, but now it is time for me to explain light speed and light travel.
Let's say this spot is Proxima Centauri, the nearest solar system, and that spot is Earth. The distance between these two celestial bodies is 4.2 light years away. Let's have light travel across the distance from this solar system to our home planet. Notice how it's taken a really long time? Should take about 4.2 years to get to the other side. Now obviously I'm not going to make you sit here for 4 years, but that's why light years are called light years. It takes a year for light to travel the distance. Now here's another thing. Let's say you were spontaneously transported to Proxima Centauri and you were looking at Earth, and you had some kind of hyper advanced telescope that allowed you to see yourself on Earth. You would be able to see yourself from 4 years ago. Now it's time for me to explain the Doppler effect. Now, here's the light spectrum one more time. I've already talked about this. Visible light, invisible light, the basics. Now, for an object to be affected by the Doppler effect, it needs to be 1, really far away, and 2, really, really fast. And by far away, I mean hundreds of light years away for us to notice any difference. Typically, objects are about the center on the light spectrum. Nothing interesting, nothing special. For example, let's say the circuit board. It's nothing special about it. It's not shifting to any side of the light spectrum. When an object moves really fast, it shifts on the light spectrum. So it could become more red or more blue depending on where it's going. If it's turning more red, then it means it's getting close to us. If it's turning blue, it's getting farther away from us. So another thing is that if it's moving fast enough, it could actually shift into invisible light ranges. For example, the invisible planets that I mentioned earlier, they're moving so fast we can't see them. A good example for this effect would actually be ambulance sirens, because this effect doesn't just affect light, it affects sound too. I have said effect way too many times in that single sentence. Now, let's say you have an ambulance right beside you with its sirens going up. You're probably going deaf, but that's fine. It's part of the experiment. It's at a normal pitch when it's right beside you. But when it starts to get farther and farther away, the pitch changes. It becomes weird sounding, like higher pitched, you know? It starts to sound off the further and further away it gets. That's because of the distance it has to travel. It shifts because of it.
So it moves so fast it goes off of the spectrum and we can't see or hear it.
In a nutshell, yes. Now you want to hear something super interesting?
Like what I haven't been listening to already wasn't already super complicated.
No, but seriously, this will be quick. Watch this video that I prepared for this very, very specific reason, and not for any other reason at all. Now look here. We're right in front of Sagittarius A right now, which is the black hole we took a picture of a few years ago. Now, like most black holes, its gravitational pull is so strong nothing can escape it, including light. And because all the light's going straight into the event horizon, that means no light is bouncing off of it. That's why they're black. There's no light allowing us to see it. Now, if you were to watch a video on entering a black hole, you would notice that there's this weird ring around the black hole. That ring is actually from light that's escaping the black hole, gets slingshot around, and allows us to see what's behind the black hole. They're strong enough to bend lights. Now, the unfortunate bit is that the the light's all distorted and stuff like that, so actually using it to see behind the black hole is kind of pointless. You might as well go around the celestial object. Now, that's all the time I have before I eventually get spaghettified, so I should probably leave. Bye. Now, I have one more thing to say before I have to end the segment off, and that is more of a mistake I've made about light than anything else. Don't think of light as a single beam of lights, or just a handful of beams of lights that just bounce everywhere. It's more of this, let me see what an uncountable amount of continuous streams of light that are being bounced around everywhere, and is also impossible for humans to comprehend because of how much there are, and because of how much mayhem there is for this light. The reason why we depict it as a singular beam of light is because it's really easy for us to imagine it as that. Sort of like the depiction of an atom, despite how inaccurate it is. So just to recap, the farther something away is, the more of this past we can see. The faster something moves, the more it will shift on the light spectrum, causing it to change colors or eventually go invisible. And lastly, black holes are strong enough to bend light and potentially catapult it across it, allowing us to see its backside. That's all I can provide for you today. However, to the next episode, we will be talking about the most underrated science ever, buoyancy, on the next episode. Bye.
So this is supposed to not be overwhelming.